Good afternoon. This file contains the pre-lecture slides for class on Tuesday, November 5th. The relevant carry reading includes several non-sequential sections from Chapter 11 as below. We've reordered this chapter to try and present related ideas together in each pre-lecture for this week. Unfortunately, this does mean you may have to jump back and forth in the textbook as you're reviewing for Tuesday's class. So for today, we begin our discussion of the last type of functional group we will cover this semester, the aromatic system. Aromaticity is a special chemical property of a compound that involves ring systems. In this pre-lecture, we will explore the concept of aromaticity and its effects on chemical and physical properties of a molecule. To do this, we will review Huckel's rule and investigate the structure and properties of benzene, one of the simplest aromatic molecules. So let's begin with the concept of aromaticity. Aromaticity is a special case of thermodynamic stability that occurs in cyclic conjugated systems. Molecules that have aromaticity are called aromatic compounds. This adjective aromatic was applied to these compounds due to the fact that many aromatic compounds are volatile and have quite distinct odors. Benzene is probably the best known aromatic compound, and we will explore its characteristics extensively in this pre-lecture a little later. So, to be aromatic, a molecule must obey three specific rules or have three specific properties. First, it must contain a cyclic conjugated polyene. Second, it must be planar. Third, it must obey Huckel's rule, which I will introduce on the next slide. Note that there are three particular descriptive words related to these three rules. We call aromatic compounds those compounds that obey all three of the rules. Non-aromatic compounds violate rules 1 or 2. Anti-aromatic compounds obey rule 1 and 2, but violate rule 3. So, what is rule 3? Rule 3 is Huckel's rule. Huckel's rule states that any aromatic compound must be cyclic planar and possess pi electrons with 4n plus 2 as their total number. Huckel's rule is violated in any case where n does not equal a whole number. So we can see that there are many molecules that would obey Huckel's rule in cases where n is a whole number. N can be 0, 1, 2, 3, 4. N equals 1 when there are 6 pi electrons, and this is the case with benzene, as we'll see a little bit later. So, here on the slide, we can see two examples of compounds that do and do not obey the three rules. On the left is benzene, which is an aromatic system. Note that it is a conjugated system, it is planar, and it has 6 pi electrons. On the right, we have cycloheptatriene, which contains 3 pi bonds as well, but note that these are not fully conjugated together. Two of the pi bonds are separated by an sp3 hybridized carbon right here. This disrupts the cyclic conjugation of the system, thus we violated one of the first two rules, and this compound is not aromatic or non-aromatic. Note here on this slide we can see examples of molecules that contain cyclic conjugated polyenes yet violate Huckel's rule, unlike benzene. When planar, cyclobutadiene on the left and cyclooctatetraene on the right are anti-aromatic due to the fact that they do not contain 4n plus 2 pi electrons. When non-planar, we would say that these compounds are not aromatic because they would have violated one of the first two rules. Most of the examples of aromatic compounds that you will see in 232 include cyclic hydrocarbons such as benzene, toluene, and naphthalene. Note that naphthalene contains two rings, but when viewed as a single conjugated pi system, we can see that it obeys all of the requirements for aromaticity, as it has a cyclic conjugated system, it is planar, and it contains 10 electrons, which obey Huckel's rule. Although most of the examples we will review will be hydrocarbons, it's important to note that heterocycles can also be aromatic. The most common aromatic cycles you will see in this class include pyridine, pyrrole, furan, and thiophene. In each of these four heterocycles, note the location of the lone pair drawn on the heteroatom. When drawn inside the ring, we are indicating that a lone pair is part of the conjugated pi system, as in pyrrole, furan, and thiophene. When drawn outside the ring, we are indicating that a lone pair is not part of the conjugated pi system, like in pyridine, furan, and thiophene. Let's take a closer look at the location of those lone pairs to be sure we understand when we include it in the pi system and when we do not include it in the pi system to determine whether a heterocycle is aromatic. Here with pyridine, we can see that there are 6 pi electrons in the ring. 2 in this bond, 2 in this bond, and 2 in this bond. The lone pair on the nitrogen is drawn outside of the ring to indicate that although the lone pair is in an sp2 hybridized orbital, it is not part of the pi ring system. It is projecting outside of the ring and is thus not conjugated with the other 6 pi electrons. Thus we obey Huckel's rule and pyridine is aromatic. Here in pyrrole, we can see that a lone pair is included in the pi system. In order to have 6 pi electrons and obey Huckel's rule, we must include the lone pair as part of the conjugated pi system. This does mean, of course, that the lone pair is located in a p orbital in order for it to overlap with the pi ring system in the ring. Furan has 2 lone pairs. One lone pair is considered to be inside the ring. One lone pair is considered to be outside of the ring. This means that one lone pair is in a p orbital and is part of the conjugated pi system, while the other lone pair is in an sp2 hybridized orbital projecting outside of the ring and is not part of the pi system. In addition to heterocycles, also note that cyclic ions can be aromatic. Here we see that although neutral cycloheptatriene is non-aromatic, the cycloheptatrienyl cation is aromatic. With the formation of an sp2 hybridized carbocation, all carbon atoms in the ring become planar and the allylic position of the carbocation completes the conjugated system, rendering this ion aromatic. It doesn't matter that it has a positive charge because that positive charge is dispersed over all 7 of the carbon atoms in the conjugated pi system. As such, this is a very, very stable carbocation. So too, anions can be aromatic when the lone pair electrons also become part of the pi system. In this example, we can see that the cyclopentadienyl anion, which contains 6 pi electrons, is dispersed over 5 carbons in the anion. This anion is thus stabilized through electron delocalization in exactly the same way that a cation would be. Although carbanions are normally sp3 hybridized, in this case we observe sp2 hybridization that allows the lone pair to become part of the pi system when placed into the lone p orbital. Due to the fact that the conjugate base of cyclopentadiene is aromatic, we observe that the parent compound is actually a weak acid of pKa 16. That means that the allylic hydrogens in cyclopentadiene have the same acidity as the hydrogen on any alcohol that you've seen this semester. This is interesting because recall that for most hydrocarbons, they're not acidic at all. In this case, we have allylic hydrogens that are even more acidic than a terminal alkene due to the stability gained by the aromatic conjugate base. This returns us to the last of the 6 principles in our I-share mnemonic, aromaticity. Compounds are acidic in any case where their conjugate bases are aromatic. This is not to say that aromatic compounds themselves are acidic. Rather, any compound that has a conjugate base that has aromaticity can be considered acidic. Before we move on to examine the physical and chemical properties of benzene, let's take a moment to consider why aromaticity is important to learn. I think the best example of the relevance of aromaticity can be found in biomolecules. It just so happens that all 4 of the bases that are used to make up DNA are aromatic compounds, as you can see here on this slide. Note that each base is a cyclic conjugated heterocycle that contains 4n plus 2 pi electrons. Because the bases are all aromatic, they efficiently stack together to maximize their van der Waals interactions. It's the aromaticity of the bases that is one of the main driving forces that produces the famous double helix structure of DNA. Aromatic groups can also be found in proteins in your body. In fact, 4 of the naturally occurring amino acids contain aromatic side chains that help stabilize protein conformations. These 4 amino acids can also be found in some of the active sites of enzymes where their aromaticity provides specific acid-base reactions. Aromatic rings are also found in the heme group in many proteins such as hemoglobin. Note here the large porphyrin ring that surrounds the iron atom in hemoglobin is aromatic. This aromatic ring helps drive the redox reaction that allows the iron atom in hemoglobin to bind and release oxygen, which is a vital process in metabolism. So with that in mind, let's take a closer look at benzene to understand the special properties of aromaticity and how they affect a molecule's chemical and physical properties. In the 1860s, Kekulé proposed a structure for benzene that included a 6-membered ring that contained 3 double bonds which alternated with 3 single bonds. Because Kekulé knew that single and double bonds had different lengths, he proposed that benzene must rapidly interconvert between 2 structures that differed in the location of the double bonds around the ring. Given Kekulé's proposal, many claimed that benzene would produce constitutional isomers upon halogenation, as we see here. However, no constitutional isomers have ever been found of benzene. This brought about serious challenges to Kekulé's original proposed structures for benzene. Later structural studies of benzene revealed that Kekulé was indeed wrong. He was right that benzene was a cyclic structure. However, structural analysis revealed that all of the 6 bonds in benzene are of equal length. This can only mean that the double bonds and single bonds are more similar than Kekulé actually realized. In fact, the length of all 6 bonds in the ring of benzene is the average length of a single bond and a double bond combined. This suggests that all 6 bonds around the ring have some single bond character and some double bond character to them. That is, the aromatic ring in benzene does not have distinct double and single bonds, but more of a blend between the two. In some sense, Kekulé was almost right. However, instead of the 2 structures he proposed at equilibrium, we now consider benzene to be 2 resonance contributors that form one resonance hybrid, where all 6 pi electrons are delocalized over all 6 carbons in a benzene ring. Today we use this structural diagram on the slide, a hexagon with a ring in the center, to indicate the delocalization of the 6 pi electrons in benzene. Given what you know about the added stability from electron delocalization, as we've seen earlier in the semester, you should be able to predict some of the effects of aromaticity in benzene on benzene's chemical and physical properties. Foremost, let's consider the effects of aromaticity on the stability of benzene. Once again, we consider the heat of hydrogenation to determine how stable benzene is. If we hydrogenate all of the pi bonds in benzene, we produce 208 kilojoules of heat. If you can recall the value of the heat of hydrogenation of one single double bond, this value should surprise you. What is notable about this value is that it is actually much less than what we would expect from the hydrogenation of 3 independent double bonds. In fact, it's even less than what we would expect from hydrogenating a conjugated diene. This extra stability in benzene comes from the fact that it is aromatic. Those pi electrons are delocalized around all 6 of the carbon atoms in the benzene ring, thus making the molecule much lower in energy than we would expect from that number of pi bonds. Note that the extra stability from aromaticity is dependent upon the cyclic nature of the aromatic molecule. Because benzene is cyclic, its heat of hydrogenation is much less than it would be were it an acyclic structure. Note here that the heat of hydrogenation of benzene is much less than the heat of hydrogenation of 1,3,5-hexatriene. Although that molecule also contains 3 conjugated double bonds, just like benzene, it is acyclic. The cyclic nature of the aromatic compound allows the electrons to freely distribute over all 6 carbons equally, thus producing a much more stable molecule. Given the delocalization of the pi electrons around the ring, we can see that there is high electron density above and below the plane of the ring, but little electron density around the perimeter of the ring. We end this pre-lecture by reviewing the rules for naming benzene rings. Thursday's pre-lecture will begin to explore some of the chemical reactions that involve benzene rings in benzylic positions. So, to name a benzene ring, we first consider that benzene is the parent and it comes last in the name. We're going to list all the substituents around the benzene ring in alphabetical order, as we would in any case using the IUPAC naming system. And we're going to number the ring in the direction that gives the lowest locant to the first point of difference in the benzene ring. So let's look at some examples. Here we see benzene is considered the parent and comes last in the name. So in a monosubstituted benzene ring, we can see bromobenzene, tert-butylbenzene, and nitrobenzene. In cases where we have polysubstitution around a benzene ring, note that we list each of the substituents in alphabetical order. Here we have 3 halogens around a benzene ring: bromine, chlorine, and fluorine. As such, we would label them 2-bromo, 1-chloro, 4-fluorobenzene. Benzene rings have alternative terminology in order to indicate the locants for di-substituted derivatives of benzene. Any di-substituted benzene rings that have 1-2 relationships are called ortho-substituted benzenes. Any di-substituted benzene rings that have 1-3 relationships are called meta-substituted benzenes. And lastly, any 1-4 di-substituted benzenes are called para-substituted benzenes. Here are 2 examples using this nomenclature for benzene rings. On the left, we see O-ethyl nitrobenzene. Because there's an O prefix, we know that this is a 1-2 relationship between the ethyl group and the nitro group. On the right, we see M-dichlorobenzene. Because there's an M prefix in front of the name, we know that the 2 chloro groups have a 1-3 relationships because they are meta to one another. Lastly, there are several structures that contain benzene rings which have unique names. Unfortunately, there's no IUPAC naming system for these, and they have to be memorized. A benzaldehyde molecule is a benzene ring that contains an aldehyde substituent. Benzoic acid is a benzene ring that contains a carboxylic acid substituent. Phenol is a benzene ring that contains a hydroxy substituent. Styrene is a benzene ring which contains a alkene substituent. Aniline is a benzene ring that contains an amine substituent. And lastly, anisole is a benzene ring that contains a methyl ether substituent. Be careful with 3 easily confused names concerning benzene rings. These are phenyl, phenol, and benzyl. Phenyl refers to a benzene ring as a substituent. This is a phenyl group. Phenol is a specific molecule. Recall, it is a benzene ring with an OH group substituent. Lastly, benzyl refers to any carbon that is attached to a benzene ring directly. Recall last week you learned about allylic carbons. Allylic carbons, remember, are any carbon atom that is bonded directly to a vinyl carbon. Here we see that benzyl carbons are any carbon that are directly bonded to benzene rings. Students often get these 3 names confused with each other due to the fact that they sound very similar and they refer to very similar atoms or groups of atoms related to benzene molecules. Spend some time differentiating between the 3 of them so that you can be sure to use the nomenclature correctly in class. With that, this pre-lecture is concluded. As always, be sure to review the relevant reading in Carry and come to class prepared to apply what you've learned.